lesson is on convergency. We shall shortly start to look at maps and charts and try to understand why certain projections are better suited for some applications and other projections are better suited to other applications. We now need to go back to slightly more theoretical studies in order for you to understand some of the concepts we shall need to look at when comparing projections. The topics that we shall study are convergency, conversion angle, departure, scale, and orthomorphism. When we have covered these 5 topics, we shall then be better equipped to compare the Mercator projection, the Lambert's conic conformal, the polar stereographic, and the transverse and oblique Mercator projections. This lesson will describe convergency, which can also be called Earth convergence. Convergency results from the fact that, except at the equator, meridians are not parallel to each other. Meridians originate from a pole, then diverge to reach their maximum distance apart at the equator, then converge back to meet together at the other pole. This means that their angle of inclination to each other is constantly changing. If tangents are drawn to the 2 meridians at the equator, they will be parallel lines in space. At the pole, however, they will converge at an angle equivalent to their difference in longitude. Looking directly down on the pole, there are 360 degrees of angle, and there are 360 degrees of longitude, 180 east and 180 west. Therefore, their angular difference is the same as their change in longitude. At some intermediate latitude, neither polar nor equatorial, the tangents meet in space at some intermediate angle, neither 0 nor the full change of longitude. This angle is known as convergency, or Earth convergence. Convergency is defined as the angle of inclination between 2 selected meridians measured at a given latitude. Both of these elements are necessary to define convergency. For instance, this diagram shows a change of longitude of 60 degrees, and the convergence at the poles is therefore 60 degrees. But if the change of longitude between the 2 meridians had been 40 degrees, the polar convergence would have been 40 degrees. Change of longitude is therefore a necessary part of the definition. However, latitude is as well. For the same change of longitude, the convergency at the equator is 0. At a higher latitude, it becomes an angle of inclination. And at the pole, it has the same value as the change of longitude. Therefore, convergency depends on both latitude and longitude, and both are part of the definition. We can derive a formula to calculate convergency. In order to do this, we will start by comparing convergency at the equator and at a pole. Let's choose 2 meridians 60 degrees apart and draw up a table. The positions we shall choose are the equator and a pole. Latitude at the equator is 0, and latitude at a pole is 90 degrees. The change of longitude in each case is 60 degrees. At the equator, the meridians are parallel. Their inclination to each other, or convergency, is 0. But at the pole, they meet at an angle equivalent to their change of longitude. Divide the convergency by the change of longitude in each case. At the equator, this is 0 degrees of convergency divided by 60. The answer is 0. However, at the pole, we have 60 degrees of convergency divided by 60 degrees of change of longitude. The answer is 1. Look at these angles and these numbers. This is a sine relationship. Here is a sine curve. Let's look at some of the more common values of sines of angles, because these are the ones that frequently come up in questions on general navigation. The sine of 0 degrees is 0. The sine of 15 degrees is about a quarter. The sine of 30 degrees is a half. The sine of 45 degrees is 0.7071. The sine of 60 degrees is 0.866. And the sine of 90 is 1. The relationship between convergency and change of longitude is therefore defined by the sine of the latitude. This gives us the basic convergency formula. Convergency equals change in longitude times the sine of the latitude. Let's now look at what the convergency will be at 30 north, between two meridians 40 degrees of longitude apart. Let's take the tangent at the meridian at 30 north. This is shown by the line X. At Y, the tangent looks like this. Let's make a copy of X and move it to Y, keeping it parallel. This will make it easier to see the angles. Their inclination at Y is the convergency. The formula will tell us what this angle is. The equation is convergency equals change in longitude times the sine of the latitude. Substitute in what you know. The change of longitude is 40 degrees. The latitude is 30 north. And the sine of 30 degrees is 0.5. So the convergency in this example is 20 degrees. We now have a formula for calculating convergency. However, it might not be immediately obvious why a pilot should wish to know what the convergency between two meridians at a particular latitude is. This might be fascinating stuff to a cartographer, but why is it relevant to practical flying? To answer, we need to understand that true north at any point is the direction of the local meridian. For example, if you fly to a different meridian from the point at which you started, your local direction of true north has changed. This is the reason why a run line is a continuously curved line on the Earth's surface. If it did not constantly curve, it could not cut all the meridians, which are at different angles to each other, at the same track angle. However, modern navigation systems such as FMS, INS and GPS use automatic computing to continuously fly the Great Circle track, because in reality it is shorter. Look at the situation on the diagram. An aircraft leaves position X, where the track angle, measured with respect to the local meridian, is as shown in blue. It flies across to position Y using the Great Circle track. Its track with respect to space has not changed. A great circle is a straight line in space. However, its track angle with respect to local north has changed because the two meridians are not parallel to each other. Local true north at position Y is defined by this line. The difference is the convergency between meridians X and Y. This is shown by the yellow shading between the two red lines. Because we are flying from west to east in the northern hemisphere, the direction of true north has moved anti-clockwise with respect to space, from line A to line B. Because we measure clockwise in navigation, the track angle as measured on Earth has increased. That is why great circle track angles change, and it explains the reasons for the rule that you learnt at the start of the course for working out change in direction of a great circle track. If you remember, we drew a circle and divided it into 4 quadrants. The top and bottom of the circle represent the northern and southern hemispheres, but the left and the right are not Earth hemispheres. They represent the direction of travel. The left side represents a westbound track, and the right one an eastbound track. Then we added the letters D-I-I-D to represent the words decrease, increase, increase, decrease. To show that if, for instance, we have an eastbound track in the northern hemisphere, the great circle track angle will increase. Just as it did in this example, it increased from track angle A to track angle B. This allows us to arrive at a second definition of convergency. In addition to being the angle of inclination between two selected meridians measured at a given latitude, convergency is also the change in great circle track direction between 2 points. We also have to modify our formula slightly because in this case the two meridians are not crossed at the same latitude. Unless flying due east or west, there will be some element of north or south change of latitude between the meridians. In this case, we cannot use the simple convergency formula of change of longitude times sine of latitude because there are 2 latitudes to consider. Instead, we take the sine of mid-latitude or of mean latitude, which with only 2 points is the same thing, to give us the formula convergency equals change in longitude times the sine of the mean latitude, where mean latitude is the mean or average latitude between the 2 points. What we have just found is the basic convergency equation. However, you may get questions which require you to transpose it. For instance, in one of the examples which follows, you will have to calculate the change of longitude. So you will have to make it the subject of the equation. You could also be asked to calculate the mean latitude. Again, it's only a simple transposition. Let's try some practical examples. Here is a typical problem. The initial great circle track from A, which is at 40 north and 2 west, to B, at 50 north and 10 east, is 060 degrees true. What is the initial great circle track from B to A? Start by drawing a diagram. It is only a sketch to get the situation in your mind, not a scale drawing. We are in the northern hemisphere, so draw 2 meridians converging northwards like this. The initial great circle track from one of them is 060 degrees true, so make it the left-hand one. because if you draw it from the right, it goes off the diagram. So choose the other one. The track originates from A on 0, 6, 0. This means that the left-hand one must be A and the right-hand one B. Check it out by reference to the latitude and longitude. If we've got it right, with an initial track of 0, 6, 0, B should be north of A. It is. It's 50 north, where A is 40 north, and B should be east of A. It is. It's 10 east, where A is 2 west. Now that we've got the diagram right, we can start to calculate the convergency. Remember, the question is, what is the initial great circle track from B back to A? Convergency equals change in longitude times the sine of the mean latitude. The change in longitude is from 2 west to 10 east. That's 12 degrees. The mean latitude is 45 north. That's halfway between 40 and 50. The sine of 45 degrees is 0.7071. So the convergency is 8.5 degrees. Now there are two ways to solve this problem depending on which definition of convergency you prefer. If you use the definition that convergency is the change in great circle track direction between 2 points, then the great circle track has changed 8.5 degrees between A and B. It left A on a track of 0, 6, 0. So using the DIID rules for increasing or decreasing track, we are looking at a track going eastwards in the northern hemisphere. The track angle will increase. That makes the track at B 068.5. If the track angle onwards at B is 068.5, then the track angle from B back to A, measured at position B, will be the reciprocal. You add 180 degrees. This makes the initial great circle track from B to A 248.5 degrees true. Alternatively, if you prefer the definition that convergency is the angle of inclination between two selected meridians, then we can do it this way. Draw in a construction line at B parallel to the meridian at A. The meridian at A and the construction line are parallel, so the angle N is also 060 because it is a corresponding angle to the initial great circle track. Therefore, the angle from the construction line round to the return track B will be 060 plus 180, an angle of 240 degrees measured from the parallel construction line. However, the parallel construction line is not local true north. That is defined by the meridian at B, and it differs from the parallel line by the amount of convergency, which, as we know, is 8.5 degrees in this case. So the initial great circle track from B to A is also 248.5 by this approach. Here's another practical example. The initial great circle track from C, which is at 36 north, 15 east, to D, which is at latitude 42 north, is 300 degrees true, and the final great circle track is 295 degrees true. Firstly, what is the longitude of D? Secondly, what is the great circle track direction at longitude 11 degrees east? As always, you must start with the diagram. We are in the northern hemisphere, so again, draw two meridians converging northwards like this. The track from C is 300, so make it the right-hand side, otherwise it will go off the diagram. This means that the left-hand side must be D. Again, check it out for common sense. If it's a track angle of 300 from C, then D must be northwest of C. If you can't see how to start, then write down the convergency equation and substitute in what you know. The way to solve it then usually becomes obvious. Do we know the value of convergency? Yes, we do. The track angle has changed by 5 degrees. So we can write the convergency as 5 degrees. Do we know the change in longitude? No, that's what the question is asking. Do we know the mean latitude? Yes, we do, because they've given us the start and finish latitude. It's halfway between 36 and 42 north. It's 39 north. Rearrange the equation to make the change in longitude the subject. And you get the answer that the change in longitude is about 8 degrees. The question has told us that the longitude of C is 15 east and D is 8 degrees further west. So what is the longitude of D? It's 7 degrees east. That's the first part solved. The next question is, what is the great circle track at 11 east? Draw it in. 11 east is 4 degrees east of 007 east, and it is 4 degrees west of 15 east. Therefore, it must be the mid-meridian, as it's halfway between the meridians C and D. So if the track is 300 at the start and 295 at the end, what will it be exactly halfway? 297.5 degrees true. Now on for you. The initial great circle track from H at 40 south, 170 west, to G at 45 south, 174 east, is 250 degrees true. What is the initial great circle track from G to H? What's the first thing you have to do? Are we in the northern or southern hemisphere? We are in the southern hemisphere, so draw in some lines converging southwards. The question says that the track leaves H on 250 degrees true to meet G. So which one is G and which one is H? H must be on the right and come across to meet G on the left. Now put in the latitudes and longitudes and check it out for sense. H is at 40 south. G is at 45 south. Does this look right on the diagram? Yes, it does. The diagram shows G to the south of H. H is at 170 west and G is at 174 east. However, on our diagram, why is west out to the right of east? That's not how we normally see it. The reason, of course, is that we are looking at a situation based on either side of the Greenwich anti-meridian, not the meridian. Our two longitudes are either side of the 180 degrees east or 180 degrees west, which is the same thing. Take the shorter departure between the two longitudes in this case the one crossing the Greenwich antimeridian. In other words, the change of longitude is 16 degrees, not 344. Now substitute in what you know. So, how much has the great circle track angle changed between G and H? What's the formula? It's the convergency formula. Convergency equals change in longitude times the sine of the mean latitude. Now put in the figures you know. We know the change of longitude. It's 16 degrees. We know the mean latitude. It's 42.5 south. Now use a calculator to work out the convergency. You find that the convergency is 10.8 degrees. So the great circle track angle has changed by about 10 degrees. Which way? Has it become about 240 or about 260? How can we find out? Use the DIID rule. We are flying westwards in the southern hemisphere. The track angle must be increasing. Look at the diagram for confirmation. The left-hand meridian is further anti-clockwise than the right-hand one. This means that when you measure a track angle clockwise from it, you will get a greater angle. So the westerly track angle at G is 260.8. What does that make the easterly track angle at G, the initial great circle track from G to H? 080.8. You apply 180 degrees of difference for a reciprocal track. It's just the opposite direction to 260.8 degrees. Alternatively, you could have used the method of paralleling the meridian. Here is the paralleled meridian. This is the corresponding angle of 250 degrees true. So what will be the reciprocal track from the parallel construction line be? 070 degrees true. However, this is from the paralleled construction line. We now have to add the convergency in order to measure from local true north. So the initial great circle track from G to H is 080.8. Let's summarize what we've covered. Convergency, or Earth convergence, results from the fact that, except at the equator, meridians are not parallel to each other. Convergency is defined as the angle of inclination between two selected meridians measured at a given latitude. Convergency is also the change in great circle track direction between 2 points. The formula to calculate convergency is convergency equals change in longitude times the sine of the mean latitude. For questions involving return initial great circle tracks, work out what the final track will be and then reciprocate it. Alternatively, use the method of paralleling the meridian. For other types of question, write down the formula and substitute in what you know. The answer will usually drop out.